What we're going to do is add, at the end of each layer, a new little function, which is going to be a nonlinearity. So we're going to take x coming in, we're going to go ahead and do xw plus b, and then we're going to apply a nonlinearity. Think of this as a little pipeline. And then that nonlinearity, we're going to go ahead and feed in to a, so this is, let's say, w1 plus b1. This is our nonlinearity. I'm going to call it g1. And then we feed it into another xw2 plus b2. And then as long as we add a nonlinearity, we're good. And in this way, we're going to be able to actually use this depth. So this depth, this number of layers, is when we talk about deep learning. That's where the deep is, because we have deep layers. Originally, neural networks only had a couple layers in them. It was very hard to figure out how to train anything deeper than that. It's over the last, let's say, 10 years mostly, 10 to 15 years, where we've really learned how to work with deep neural networks. So what's this nonlinearity going to be? Okay, so what's g, our nonlinearity? Our nonlinear function. Well, we have some choices. What are some we've seen? We could use a sigmoid. And that's often used, actually, at the very last nonlinearity. By the way, these nonlinearities, we're going to call them activation functions. And we're going to represent them with a g. So one kind of an activation function is a sigmoid. Sigmoids are often used as activation functions at the end of the last layer. What situations? Well, if you're doing binary classification, for example, so here if you have one output, so this is a 1 by 1 as the final here, then we'll do a sigmoid on that, and that'll give us the probability that it either is or is not of that binary class. Or if we're doing multi-label classifications, then we might have a sigmoid that applies to 1 by some number of elements. Let's say we've got 10 classes that or 10 labels we're using, then we'd have a 1 by 10 out here, and we'd apply the sigmoid to each of those 1 by 10. So that's common. Another one that's common is a softmax. That's also common, though, only at the last layer. So if we have multi-class classification, we would have a softmax, and that would take care that we had numbers between 0 and 1, and that their sum was 1. So good to use for probabilities. These are not used, though, as internal activation functions. There are better ones. So we have, historically, we use tanh. So tanh looks like basically a type of a sigmoid function. But instead of being between 0 and 1, it is actually between -1 and 1, and looks kind of like this. So it's really a stretched out sigmoid function. Well, stretched out and translated sigmoid function. So for tanh, it takes on values from between -1 and 1, and at 0, it's equal to 0. So this, historically, was what was used as activation functions between these layers. It turns out something simpler will work. So let's look at what this something simpler is. It's called a ReLU, which stands for a rectified linear unit. Let's first look at what a rectifier is. So looking things up, a rectifier actually is used for AC to DC conversion. And so what happens in a rectifier is if we have a sinusoidal AC, something like that, a rectifier will chop off any negative values so that we end up with something that looks like that. So we just go down to 0 and over on 0, and then up and down to 0 and over on. I'm not sure how that's used in AC to DC conversion, but this is a rectifier. So this is a rectification, if that's a word, of a sinusoid. let's look at a rectified linear. So if we've got a linear function, and let's just say that this linear function is in fact the identity. Well, what does the rectifier do? The rectifier gets rid of anything that's less than 0. So we have a function that looks like if x is negative, it's 0, and if x is positive, it's x. So this can easily be written as the max of 0 and x. Okay, again, if x is negative, then the max is 0. If x is positive, the max is x. This is a real U. Is it nonlinear? Well, yeah, barely, but yes, it's nonlinear. This is the most common activation function that we're going to be using between layers here. So basically, we're going to take an xw plus b, and then we're going to take a max of 0 and x coming out of there. And then we're going to do a different x, w and b, and then again a rel u. A different w and b and a rel u. And that gives us a neural network. And at the end, often we don't use a rel u. So you might use a rel u as an output activation function. For instance, let's say you're predicting house prices. Okay? No house prices are ever negative. And so therefore, you could go ahead and use a rel u as the output. And that way, the output of your neural network is guaranteed, even when you have your initial random weights, to be non-negative. There is a version of a rel u called a leaky rel u. So a leaky rel u looks like this. It is equal to x when x is greater than or equal to 0, and it's equal to some fraction of x when x is less than 0. So it's basically equal. So it's the max of some, let's say, rho of x, where rho is a hyperparameter. And it's less than 1. So it's often maybe 0.01, something like that. Okay, why do we care about this? We're going to see that the derivatives of things matter. So we have a derivative of 1 here for a rel u, and that's kind of nice, but it goes to 0 if x is less than 0. We are going to, this is looking ahead a bit as we look at what's called backpropagation. Backpropagation is really just the idea of calculating the gradient and using the chain rule. But as we're calculating the gradient, we have to multiply by the chain rule by the intermediate gradients. And in particular, we want to look at the gradients of the activation functions. And so the gradient of this is, when x is greater than 0, is 1. That's actually much better than tan h. So if we looked at tan h, right, when x is large, the slope is close to 0. When x is small, the slope is close to 0. So only when x is in a small range do we actually have a useful gradient. Now the problem is, if we have any of these gradients are 0 or close to 0, then the entire gradient going back, let's say to here, would be multiplied together. We have to go through each of these activation functions, and so we'd end up with a 0 gradient here. So it's hard to train this layer. So the move from tan h to rel u, or in this case leaky rel u, meant that the gradients of these were, as long as x was non-negative, or as long as x was positive, then these gradients were 1, okay? Which meant even if you multiplied together a bunch of them, you'd still get a value that was 1. So we're looking ahead. This is sort of a preview of vanishing gradients. And the way I think about these in some ways is rel u is, although it's nonlinear, it's sort of the simplest nonlinearity you have, right? Because what we're doing is we are taking a linear function and we're just bending it. So it's sure close to linear, very closer to linear than, let's say, a sigmoid, which is a curve and smooth and so on. So it's surprising in some ways, that this simplest possible nonlinearity still leads to the ability to build neural networks that can do all sorts of neat things.